Thank you for participating in today's Solar Decathlon virtual session, which will address shining a light on solar, a tour of cutting-edge solar research with the U.S. Department of Energy. My name is Jonathan Cohen, and I work on the Solar Decathlon, as well as run the Better Buildings Residential Network with your Department of Energy. We strongly encourage you to ask the questions you want answers to on today's virtual session. That's why we're here. And just as a way of background, the U.S. Department of Energy's Solar Decathlon is a collegiate competition comprising 10 contests that challenge student teams to design and build highly efficient and innovative buildings powered by renewable energy. The competition features 2 tracks, the Design Challenge and the Build Challenge. The Solar Decathlon provides a hands-on experience and unique training that prepares the competing students to enter the clean energy workforce. This international competition has been a driving force in raising awareness about clean energy since its inception in 2002. We'll go on to the next slide, please. And we're going to share that we have a stellar slate of speakers from the Department of Energy's own solar office who will share their work with you. And after the end of those 3 speakers' presentations, everybody will have an opportunity to ask questions. So we do encourage you to jot those down as they come to you and be at the ready and chat them in actually as you think of them. And then we will access that chat when it comes time for questions. And we'll have a few other slides as well. And so if we go to the next slide, and we want to share that there is actually one more virtual session in this series, which has been going on since the fall. And the actual competition comes to a head in the next month, and then we will have the winning teams give tours of their houses. So do register for that and stay tuned and join us on that's Wednesday, April 26th. I believe that one will take place. But go to solardecathlon.gov to sign up. Next slide, please. And here's the functionality about how you can ask a question. You can raise your hand virtually in the upper left box to be unmuted to ask a question orally, or in the box in the lower middle of your screen, chat your question in, and then we will read those questions. So next slide, please. And now it gives me great pleasure to introduce our first speaker. Michelle Boyd is the Program Manager of the Strategic Analysis and Institutional Support Team in the Solar Energy Technologies Office, affectionately known as CETO. The team supports the development of analysis, tools, and data resources to reduce the non-hardware or soft costs of solar energy and accelerates learning through technical assistance programs and national partnerships. Michelle joined CETO in April of 2016 as a technology manager on both the soft costs and the technology to market teams. Previously, Michelle was the government relations manager at Abengoa Solar, where she developed and implemented strategies to advance effective financing, siting, and transmission policies for solar. Prior to her work on solar, Michelle focused on environmental and policy issues related to nuclear weapons, nuclear power, and nuclear waste at Physicians for Social Responsibility, Public Citizen, and the Institute for Energy and Environmental Research. Michelle has 2 Bachelor's of Science degrees in Biology and Environmental Science from Purdue University and a Master's of Science in Environmental Policy from the University of Michigan. And with that, it gives me great pleasure to introduce a colleague from the Department of Energy and a star in the solar world, Michelle Boyd. Michelle, the floor is yours.
Thank you so very much for that lovely introduction. Next slide, please. Before we get started, I just would like to give a brief overview of DOE's Solar Energy Technologies Office. The mission of the office is to accelerate the development and deployment of low-cost, reliable solar energy in the United States. In order to do this, we research photovoltaic and concentrating solar technologies and grid integration of these technologies. And we also provide support for getting new technologies to market, as well as how to reduce the non-hardware costs of deploying solar. Our projects and programs aim to reduce the cost of solar electricity for all Americans, enable solar to support the reliability, resilience, and security of the grid, and support solar job growth and manufacturing. Next slide. And I would also like to do a quick plug for our Science and Technology Fellowship at the Solar Office. This opportunity is available to scientists and engineers with bachelor's, master's, or PhD degrees of all types of backgrounds. Fellows have a really important role in establishing and implementing new projects and initiatives to make solar energy more affordable and reliable. They also learn about the federal government and its role in advancing science and technology. Applications are accepted on a rolling basis with 2 annual review dates, January 15th and June 15th, the latter of which is coming up soon. The website for more information is on this slide. Next slide. So today we're going to hear about 3 areas of research funded by the Solar Office. I will start by talking about the co-location of agriculture and solar, also called agrivoltaics. Then Andrew Dawson will discuss our research on perovskite photovoltaics. And finally, Dave Walter will talk about our research on community microgrids. Next slide. So I will focus on 4 main points in my talk. What are the land use concerns with solar? And what is agrivoltaics, and how can it help? What is the research we're doing? And then finally, what further research is needed in this area? Next slide. A relatively small amount of land is needed for solar to power the electricity needs of the world, as shown by the tiny black boxes on this map. But actually building that much solar in one place is not practical. We don't want to build over the entire Mojave Desert, for example. It is also not feasible to build transmission lines to move this electricity to everywhere. And in the United States, states determine their energy policies for the most part, and they want the jobs and economic benefits of energy production to be located in their states. Next slide. At currently projected deployment rates, solar will require 2 to 3 million acres by 2030, or just about 0.1% of the U.S. contiguous land area. Next slide. But when solar deployment is spread across the U.S., agricultural lands are often the best land for solar, flat and sunny. At the same time, maintaining a farm can be economically challenging. So when farmland is converted to solar energy production, it can lead to local concerns about the impacts on agriculture and rural communities. Next slide. The question that the Solar Office is asking is, can solar be combined on the same land with agriculture to the benefit of both agriculture and solar energy? In this work, we are defining agriculture as crops, livestock, and/or pollinator habitat. Combining these 2 land uses has created a new term, agrivoltaics. Some of the potential benefits for farmers include providing a diversified revenue stream, reducing irrigation water needs by shading the plants, improving crop yield, especially in dry or hot areas, and improving crop resistance to extreme weather, such as droughts. Potential benefits to the solar industry include reducing land use competition and making siting easier, improving PV panel performance by cooling the panels, and lowering solar operation and maintenance costs. Next slide. Here are some example agrivoltaic configurations. In the upper left-hand corner is a traditional solar array with bare ground or gravel underneath. Next to that is a traditional solar array with grasses and grazing sheep. In the upper right corner is a solar array with pollinator habitat. In the bottom row are some options with other types of solar designs that could allow for growing crops underneath, including raised panels and vertical bifacial panels, as well as different types of racking systems, such as the one shown here on stilt mounts. The idea is to design the system to enable equipment such as small tractors to have access. In other words, what agrivoltaics looks like is still being explored and will likely depend on where it is located and what kind of agriculture is being carried out. I should mention here that most work on solar with crops is focused on hand-harvested or small machine-harvested crops, not large fields of commodity crops such as corn. One reason is that would require raising the panels quite high and significantly increasing the cost of the system. Next slide. So what agrivoltaics are being done in the United States? The answer depends on the type of agriculture, but we don't have great data. Solar plus pollinator habitat is becoming more common in the US. There are over 150 facilities with pollinator habitat being grown on site, most of which are sites 20 megawatts in size or less. And 15 states have guidelines for seed mixes and management practices. So there's a lot of interest from policymakers and regulators in this option. Grazing sheep under solar panels is also becoming more widespread. The American Solar Grazing Association roughly estimates that about 12,000 to 15,000 acres of solar sites are maintained with sheep. And a few sites even have cattle grazing under solar arrays. Solar plus crops are not as far along. There is one commercial solar crop site in Colorado, but sites are planned to start in Massachusetts and California this year. Next slide. The Solar Office's flagship project on agrivoltaics is called INSPIRE, and it's led by the National Renewable Energy Laboratory. This project has been researching agrivoltaics since 2015. Research is being carried out across the country at 29 sites, including both at universities and commercial solar facilities. The project is researching such questions as the economic viability of agrivoltaics, looking at a variety of crops and configurations, increasing agricultural yields in arid environments, using agrivoltaics to improve energy, water, and food security in remote areas, such as Puerto Rico, and understanding the ecological services from solar plus pollinator habitat, such as increasing pollinator populations and local nearby agricultural productivity. Next slide. I'm going to talk about results from just two of our INSPIRE sites. On this site in Arizona, research was on crops under PV panels, looking specifically at dry lands. And what they found from results from 2016 and 2017 is that they found as much as a threefold increase in crop yield, depending on the crop type, as much as a 50% reduction in irrigation requirements, and a 2% increase in solar panel performance due to cooling of the PV panels. Next slide. Research on growing pollinator habitats under PV panels in Minnesota found 3 times more beneficial plant species, a 4-fold increase in pollinator insects, higher energy output from the PV panels, and less mowing required at the solar facilities, which can help lower O&M costs. Next slide. The Solar Office has recently expanded our work in this area, and we have selected 4 additional projects that will research other aspects of agrivoltaics. The University of Illinois Chicago will be studying pollinator plantings at very large-scale solar facilities and developing an implementation manual and tools for solar developers. The University of Massachusetts Amherst is going to study solar and crop productivity at commercial farms in Massachusetts, as well as the farm economics and public perception of agrivoltaics. Silicon Ranch is going to look at an innovative system for sustainable cattle grazing under solar panels in the pasture lands of Georgia. And then the National Center for Appropriate Technology is going to create an online clearinghouse for farmers, which will include a user forum, technical assistance, and informational resources. It will also facilitate peer mentoring and field trips to demonstration sites. Next slide. Agrivoltaics have the potential to help address land use conflicts and benefit both the farming and solar industries, as well as local communities. But there is still a lot of research needed for agrivoltaics to scale. Some of the remaining questions include the economic valuations and trade-offs. Agrivoltaics won't work unless it makes economic sense for farmers. A comprehensive assessment of the environmental and ecological impacts of agrivoltaics. Studies have just started to gather this data. animal welfare and nutrition studies for solar plus grazing, public perception of agrivoltaic projects. Will they help reduce land use conflicts? And tracking existing and future agrivoltaics projects and the lessons learned. Thank you so very much. I appreciate the opportunity to talk about this exciting research, and I will now turn this back over to you.
Great. Thank you so much, Michelle. We really appreciate that presentation. That was extremely informative, extremely well organized. And again, chat in your questions for Michelle as they come to you into the chat box. We'll pull those out later and throughout the presentations to follow. And speaking of, I'm now going to introduce our second speaker, and I'm very happy to be able to introduce, actually I have a file for Andrew Graves rather than Andrew Dawson. So I'm actually going to let Andrew introduce himself so as not to give him the wrong introduction, but want to extend a warm welcome to being on the program today. We really appreciate your time and your insights, Andrew. I'm now going to turn the floor over to you to take it away. Andrew?
Sure, thanks so much. I'm excited to be here and talk a little bit about perovskite photovoltaics. So a quick intro to me. I'm a technology manager in the office. I work a lot with our photovoltaic and manufacturing programs. My background is in mechanical engineering. I have a bachelor's from Cornell, a master's from Georgia Tech, and I've worked across a number of energy technologies for my whole career before coming to the Solar Energy Technologies office and this particular area of work. So what I'm going to go through today is just a quick introduction to photovoltaics, to perovskite photovoltaics, and then talk a little bit about why the office is interested, what challenges there are, and what we're trying to accomplish, and then a little bit about our programs and particular goals within this space. Next slide, please. So there's a few photovoltaic technologies out there. The ones that most of you are familiar with likely are crystalline silicon and cadmium telluride. So these are the two sort of large commercial technologies. Generally, if you've seen solar panels, it's very likely to be one of these two. But there are others. These others are either more heavily used for specialized markets due to their performance and cost considerations, or there's something that might be emerging. So perovskite photovoltaics fall into the second bin. They're an emerging technology, and the solar office is really looking to understand what the potential is and whether we can remove the remaining risks that would make this a commercially viable technology. Next slide, please. So perovskite photovoltaics are named after this particular crystal structure. There's actually a wide variety of formulations that fall within the perovskite photovoltaics bucket. There's some common formulations, but there's really a wide solution space here. They're typically produced as a thin film technology, which means you have a very thin layer that's put down, and then you use either a mechanical or a laser scribe to cut it into smaller cells. These are very thin layers on the order of a few hundred nanometers, which means you have very low material requirements. And it's something that you can make with a variety of methods. So you can make them using a vacuum deposition, or you can make them using solution or spray printing techniques like you'd find making newspaper or something like that. And we do see these both proposed as standalone devices, so a perovskite thin film alone, or as tandems. So this can be put on top of crystalline silicon or on top of cadmium telluride to increase the overall efficiency of the devices. Next slide, please. So why are we interested? Essentially, we've seen some very rapid progression in the performance being demonstrated by perovskite cells. So these are small cells. They're coming out of academic and national laboratory research groups primarily. You can see you've seen over the last decade a very rapid increase in efficiency. So efficiency is essentially how much of the energy that's in the sunlight hitting the cells is converted into electricity. So higher efficiencies mean you get more power out per square meter. So this is good for how much power you get from your system. This is good for the cost of your system, all those things. So we're excited to see the high efficiencies being produced out of these research groups. If you go to the next slide, Another aspect of this is also that you can, because of the deposition approaches here, that you can print them, you can spray them, you can put them on a lot of different things. So you can put them on metal foils, you can put them on plastic, you can put them on glass. And so you can actually produce these on a really wide range of form factors. They can be rigid, they can be flexible, which gives you a lot of opportunities to bring these to market. You can go to the next slide, please. And the other aspect here is something I've mentioned. It's really about how you manufacture these types of devices. So this is an image that I really like to use from the New York Times. Actually, they ran a special just on how newspapers are printed. And this type of machine, while it's certainly not exactly the same, is something that could be used to produce perovskite photovoltaic panels if we can de-risk all of the manufacturing challenges around this solution processing technique. What's interesting about that is because you can produce so many off of this single machine, you can produce the panels at a lower cost because not as much of the cost of the equipment needs to be spread across each panel. And you can build a factory for a lot less money than for some other technologies. This is all notional, right? This hasn't been proven out yet, but this is where we see some potential where we could, if we have a very low capital intensity technology where we have cheap factories, we could build more of the factories faster. So we increase the amount of solar panels we can produce each year versus other technologies. Next slide, please. Just to summarize, we're seeing this potential high efficiency. It's demonstrated at the cell scale, and we're seeing increases, continuing increases in that space. There's a lot of different market options and form factors that could be created here. And we could have very cheap panels and very cheap factories, which is a pretty compelling story. So why don't we already have perovskites on the market? You can go to the next slide, please. So there's some major challenges here. The key one for perovskites at the moment is the stability and degradation question. So essentially, perovskites are susceptible, or they have been in the past anyway, to water and to oxygen. It makes the performance degrade so that they don't produce as much energy anymore. Now, a few years ago, perovskite panels only lasted a few hours to a few days before they would degrade. And so a lot of work has been done in this space. A lot of the research groups are showing performance that's more in the range of sort of months to potentially years. However, to be competitive against other solar technologies and other electricity generation technologies in general, we really need to boost that into the decadal lifetime, right? So tens of years. And so that's a major area of research here, and it's a major challenge to still be resolved for this technology. We've used this figure in part because it shows all the challenges simultaneously, which is really how they all need to be addressed, right? I've been talking about the stability challenges, but you can't solve that challenge and then you can't solve that challenge at the expense of the other areas, right? So you can't have a very stable module that's very low efficiency and very expensive to make. That won't be a compelling case. And so really we need to address all of the three corners of this simultaneously, which I would view as the technical challenges. And then we also need to make the community aware so that people feel confident that this technology is bankable, they can rely on it if they invest in it, and that it is something that is acceptable to the community so that people are interested in putting in money to build these factories, in buying these panels when they're produced and putting them out into the field for projects. So there's a number of both technical and commercial challenges still to resolve. And it's something where we're trying to work across our portfolio and through the projects we fund to address all of these. Go to the next slide, please. Our perovskite portfolio is spread across two of our sub-programs in the office, the photovoltaics sub-program and the manufacturing and competitiveness sub-program. The reason I bring this up is just to talk about the fact that this is a really pretty broad program that runs the entire pipeline from the earlier stage R&D, where we might be looking at a very long time horizon. This is more sort of fundamental academic R&D, through to working directly with companies, startups, organizations that are trying to figure out how to manufacture and commercialize these technologies in the manufacturing competitiveness subprogram. So we have a pretty broad range of our office engaged here and a pretty broad range of our stakeholders. We work with the national labs, we work with academic R&D institutions, and we work with companies. And so we have last year we ran a large funding opportunity that was targeting sort of all the challenges I previously mentioned. And we're excited. One of the aspects of that is this validation and bankability center. That's sort of the piece that's been, I would say, less represented in our portfolio because we were trying to address more of the technical challenges early on. But we're excited to get a center running that is going to look at how we build confidence and trust in the fielded performance of these technologies. So how do we know that the perovskite modules will produce as much energy as we think they will? How do we build that trust? And that's what that center is going to be focused on. Next slide, please. So what we're trying to accomplish here is really proving out whether perovskites are going to be capable of competitive or surpassed performance as compared to our incumbent technologies. So this is silicon and CadTel, as I mentioned. And what we want to see is, are they capable of this? And then if they are, if we feel they are, how do we build confidence that this fielded performance is real? And we need to do both of those to hit the sort of overarching goal, which is to have substantial market entry in under 10 years. So in the near term, what we're looking at is this validation center I mentioned, continuing R&D across manufacturing and more academic or device R&D. Then we're going to be moving through some work around common targets, and hopefully as the risks continue to be resolved and retired, we'll be able to move further and further towards fully de-risked technology. Move to the next slide, please. So what comes next? We have this validation center that we're going to be launching shortly. We are going to be working with the community to sort of refine our messaging and what we think are the relevant performance targets that we think need to be hit and shown to demonstrate that you're on the path to commercial relevance. And we're going to be continuing to talk to the community, to everyone. I was happy to be invited to this webinar to get a chance to share with you sort of our thinking on this space, to hopefully get a few of you excited about this space, and we hope to continue our engagement and to have the opportunity to work with as many people as are interested in the perovskite space as possible. And then new programs. Certainly what we have now is not the only things we're thinking of. So we're excited. We have some new programming in the works, and hopefully in the fall we'll be able to announce a little bit of that. So stay tuned. And I hope with that I'll close, and I'll just hope that if you have any questions, you put them in the chat. I'm happy to field anything you may have. Thank you.
Okay, great. Thank you so much. That was a very interesting presentation. Again, very well organized. We appreciate the preparation that the solar team has made to share their work today. Really, really good material. And now, as we digest that presentation, move on to our third and last speaker. And I am happy to introduce David Walter, who's a technology manager for the systems integration team, and first joined CEDO in December 2016 on the technology to market team. He manages a variety of projects with a focus on power electronics, smart communities, operations and maintenance, and codes and standards. He also plays a key role in the management of the office's Small Business Innovation Research and Small Business Technology Transfer Program. Prior to DOE, he was a senior engineer for the Hartford Steam Boiler Inspection and Insurance Company, where he evaluated solar and wind installations for risk exposures from fire and operational issues, as well as provided energy yield analysis. And prior to that, he was the mechanical section leader and a pilot for the Deep Submergence Vehicle at Woods Hole Oceanographic Institution, performing research globally in depths up to 4,500 meters, which is deep. David is a registered professional engineer and project management professional, having worked in the solar, energy efficiency, deep sea research, and naval nuclear areas. He has a BS in ocean engineering from the U.S. Naval Academy, having served in the U.S. Navy as a lieutenant and assistant engineer on the USS Alabama, a nuclear-powered ballistic missile submarine. So, with that, I turn things over to David. David, the floor is yours.
Thank you very much for that introduction. So today I'm going to be discussing some of the work we're doing towards creating community microgrids. And through that, we'll go over a little bit about what does it mean to be resilient, how is solar integrated into the grid today to increase that resiliency, discuss a little bit about what a microgrid and how a community level microgrid can be a solution to help provide resilience to a system, and what research we're doing to get there. Next slide, please. So I'd like to discuss a little bit about what a resilient electrical system is and how the research we're performing here can help achieve that. Now, you may have heard about or experienced the large-scale outages of the grid due to extreme weather conditions or as a result of a cyber attack. And these weather events, such as polar vortex that happened recently in the Midwest or wildfires that occurred in places like California and Colorado, will likely to continue to get larger and happen more frequently. It's important for our grid operators to design into the system the ability to withstand these events, but also be able to recover from them quickly as well. A reliable system is made up of components that continue to work during those extreme conditions, but a resilient system can adapt and recover from those issues when those components fail. A resiliency event has several stages to it that each present its own distinct challenges. From understanding what's failing during an event through maybe the use of smart sensors, to testing the system to know what can be restored, and then being able to dispatch the right personnel to effect repairs to bring the system back to its full potential, are all different parts that potentially solar can help during each one of those stages. Next slide. Now, currently, solar plus storage batteries can be used to help a building operate during an outage, much like an inoperable power supply or a UPS. The solar panels can charge the battery and provide power while the sun's shining, and the battery can be used for when the sun's not. They can be used to supplement backup generators to reduce their fuel consumption, and as the price of solar and storage continue to drop for these systems, when they're designed properly, they'll be able to run the building for several days cost effectively. There are also ways to coordinate the use of these systems through system aggregators to reduce the power needed on the grid, so the utility can continue to provide power to customers that don't have a backup system like this and keep the grid running. Now, there's research being done in how these systems can be used to restore power, also known as black starting, sections of the grid where the power has been completely knocked out, or utilized in a microgrid. Next slide. So now that I've mentioned microgrids, let me give you some additional background information into what a microgrid is. So a microgrid is a group of interconnected loads, which are basically power users or customers, and locally based generation units that can operate on their own, like disconnected from the grid, or also known as islanded, or connected to the grid. Microgrids today typically have diesel generators or combustion turbines and are supplemented with solar, wind, fuel cells, and or storage batteries to reduce their fuel loads. There are some instances of utility-owned microgrids for small areas and neighborhoods, such as an area known as Borrego Springs in California. But the majority of installed microgrids are more of a campus level, a collection of buildings that can operate on their own and have defined areas for the area that they, boundaries for the area that they service. Now, the cost of operating a microgrid may be significantly higher than utilizing the distribution grid, but they do allow for maintaining power throughout a wide variety of conditions and give more control to the microgrid owner on the type of power they use. But what if we were able to utilize similar technology for the rest of the distribution system? Next slide. I present to you here the idea of an adaptable community-level microgrid. In this scenario, we can install enough solar and storage to provide for all the critical loads, such as hospitals, police and fire departments, etc., and provide additional power to the other customers on the system. We can define specific areas to run in distinct microgrids that are all connected to the grid, but if sections of the grid become unusable due to, let's say, a down power line or a blown transformer, the system can reconfigure itself through smart switches to route the power to the critical parts in the most efficient way possible. Now, a system like this needs a large number of components to work in unison, and that's where our office's researchers can help. Next slide. My team, known as the Systems Integration Team, works in a variety of different areas to integrate those systems to utilize solar in the most effective ways across the grid. Now, the microgrid we discussed needs to be able to run by itself, just like the distribution grid your homes and businesses are connected to, or the transmission system that feeds those distribution systems, just at a smaller scale. The controller needs to be able to forecast the amount of solar energy it will have available to it throughout throughout the day and a period of a week, as well as understanding what the power needs are for all the users that are connected to the system, and be able to prioritize the most critical pieces of that system to ensure they are operating by making sure batteries are charged when there's excess power, knowing when it needs to run a backup generator to make sure that the fuel supplies last as long as possible. There are also power electronics, which I'll go into more detail in a couple slides, that are needed to convert the power from solar panels, which is a direct current like what comes out of a battery, to alternating current, which is like what comes out of the 120 volt outlet that you have installed in your wall. There needs to be coordination with the energy storage system to ensure those batteries are charged when they're needed, and that also that they're not run so flat that they could be damaged, as well as doing the analysis to understand how big of a storage battery will be needed for that area and for how long an expected outage could be. In order to understand what's happening throughout the system, there also needs to be a robust network of sensors to communicate back to the controller what's occurring in the system. Most distribution grids today have very limited information about what power is doing throughout the grid, and sometimes it's just at the substation where it's being fed from the transmission system. And lastly, we also need codes and standards to properly integrate these systems together on a national scale. Next, I want to go into a little more detail on a couple things we are working on to make those community microgrids more of a reality. Next slide. Yeah. As I mentioned earlier, we want these microgrids to be adaptive so that they can continue to provide power regardless of what happens to the system. In order to do that, there needs to be several layers of control in the system to control what is using power and how to get it there to make sure the most critical things are serviced first and then work on down the line accordingly. Our Reorg project with the National Renewable Energy Laboratory is developing an algorithm to break the system into its smallest components, kind of like a cell, to be able to optimize what's running in that cell, such as large controllable loads, such as heating and air conditioning, as well as taking uncontrollable loads into account, like some of the lighting that is being used, or when you're plugging in computers or your coffee maker, as well as running what power generation sources are available, such as the solar and storage system or diesel generators in their most efficient ways. These cell controllers need to be able to communicate with each other to optimize the entire system and be able to share power amongst cells to service as many customers as possible. We have another project with Argonne National Laboratory, which is working on methods to reconfigure the way that separate microgrids in a system are connected to each other and determine which microgrid should take control as a leader and which controllers should then follow that leader to maximize the efficiency of all the systems running in between them. Next slide. Another area of research needed to allow solar and storage to provide most of the power to the system is in the area of grid-forming inverters. As I mentioned earlier, inverters are the power electronics that convert power from direct current from the solar panels or batteries to the alternating current, which comes from your outlet. Today's solar inverters are known as grid following, which means they need to get their frequency input from the grid and they send power back out to the grid based on the signal they receive. In today's grid, that frequency is generated by large rotating generators that are used in power plants that send the majority of the power to the grid. An inverter doesn't have moving parts in it, so they need to generate that frequency electronically by manipulating a series of switches. In a grid that's majority powered by inverters, either from solar or wind, there needs to be coordination between those controllers to properly share the load and to be able to handle the transitions between traditional generation, current generation solar inverters, and these newer designs. We've worked with the National Renewable Energy Laboratory to develop a roadmap of what's needed to move to this type of system, and with a number of institutions such as University of Washington and General Electric to develop the controllers for these new types of inverters. Our office is also in the middle of bringing together a consortium of academic institutions, national labs, and industry to develop and test electrical systems that are run by these grid forming inverters. Next slide. And finally, we're about to get started on 3 new projects to demonstrate the feasibility of these resilient community level microgrids that I discussed earlier. These projects will be serviced by a large amount of solar with storage and be able to work autonomously to reconfigure themselves to maintain critical loads running throughout any type of event, and even be able to restart sections of the grid using solar and backup power generators. Those projects are from the National Renewable Energy Laboratory, which will be demonstrating in Rolling Fork, Colorado, a system that will be able to utilize mobile storage units as well as separate controls to prepare for incoming storms and wildfires. Oak Ridge National Laboratory has a demonstration project in Adjuntas, Puerto Rico, which will be looking at a way to coordinate 3 separate microgrid controllers together, as well as integrating them with the utility grid. And the University of North Carolina, Charlotte is working with their state's energy department to develop coordination plans and test techniques in a microgrid installed in Hot Springs, North Carolina. And with that, I think it's time to turn it back over to you, Jonathan, to see what questions we have. Thank you.
Great. Thank you very much for another in a series of stellar presentations. That's really great download of the fantastic work and research that is taking place in the department's solar office. And now is the time to be able to ask the questions you want answers to on today's session. Again, here's the functionality on your screen about how to do that. You either raise your hand virtually or chat into the box by text your question. And we are now going to take questions for the rest of the way. I'm going to turn things over to my colleague Tyler to see what questions have come in over the line for Michelle, Andrew, and David. Tyler, what do we have for our colleagues?
Thank you, Jonathan. We have quite a lot, so thank you to our audience. I think I'll start with just a very broad but good question. Raylan asked if there are any limitations to using solar energy.
This is Dave Walter. I guess I could take that one. So there's definitely limitations in how you utilize solar, just in terms of you need to be able to understand what your generation potential is throughout not just the day, but throughout a week and over the course of a year. So like I mentioned, some of the work that my team does, and as well as a couple of other projects we have going on, are being able to optimize the amount of storage, as well as combining hybrid type controllers to work with wind, to work with hydro, to work with traditional generation, so that you're maximizing that amount of potential for utilizing those solar assets.
Very good. Thank you very much. A question from Robert, who asked if perovskite technology would be a good fit for covering surfaces of electric vehicles to allow for self-charging in open spaces or while in transit.
Sure. So it certainly could be, given the fact that you can make them as flexible panels, so you could make them so they could conform to a vehicle panel. I do think there are a lot of questions around vehicle integrated photovoltaics, just in terms of whether they're always in the sun, whether you can generate enough energy to reasonably offset the consumption of the vehicle. So I do think there are some general questions there, but perovskites could be a solution. Thanks.
Thank you. And a couple of additional related questions on the subject of perovskites. Felix asked, what about raw materials? How rare are they and where are they? And Chris asked if perovskite panels pose any recycling or toxicity challenges. So maybe if you just have high-level thoughts on what the supply chain for perovskites looks like.
Sure. So they're good questions. For the input materials, there's really very little that is rare or critical material. These are generally earth-abundant materials. From a toxicity perspective, it is something that we're looking to understand a little bit more. So one of the more common formulations, a number of the more common formulations contain lead. Now, this is a very thin layer, and it's not clear that the lead poses a significant risk if the panels are broken or anything like that. Certainly, while the panels are operational, the lead is fully contained. But it's something we're trying to understand, and in parallel, we are investigating a few approaches that would essentially put additional layers inside the panels such that the lead would bind to those layers versus escaping from the panel if the panel were broken. So it's something we are looking at. It's something that we are actively trying to understand. The scale of any problem with lead is not fully understood, but we're looking at a number of options.
Great, thank you. And another general question about solar overall. Raylan again asked whether living in the mountains would impact solar energy. So is there any relationship between elevation and the ability to harvest and use solar energy?
I guess I can take that one. So there is a small impact of elevation in terms of how much atmosphere the light has to get through, essentially, before it hits the panels. Living in the mountains, I would say maybe more of a consideration is whether there is significant shading. So the times of day that you are getting direct sunlight versus being in shade from a mountain nearby could influence the amount of energy you produce, when you produce that, and therefore what the right system design is, essentially which direction you point the panels.
All right, thank you. We had several questions about direct current as it relates to solar. Terrence asked, what role does the panel see for direct current in the design of future grids, in particular microgrids? And we had another question about the feasibility with local scale direct current grids, again, in microgrids or maybe just in individual homes.
Yeah, this is Dave. So for direct current microgrids, the department has been interested in looking at those off and on again. There are some instances of direct current microgrids throughout the world. Right now, though, I think it's a little more of a chicken versus egg problem in terms of having direct current appliances. So our buildings office, in particular, is looking a little bit into the development of like washing machines and dishwashers and hot water heaters that could potentially use direct current. So that would make a DC microgrid more feasible. But there are definitely some potential advantages to using a direct current microgrid or a small-scale distribution system, because you're not losing any of that energy converting from the DC coming from the solar panel through that inverter to AC. So just the efficiency gain you get there may be worth looking into. But there are definitely some research programs that are going down that path.
Great, thank you. And another one about community grids. Is there any consideration or projects right now in cold climate areas, North Dakota, Canada, Alaska, or similar, with solar plus X plus something else? It usually fails in cost-benefit analyses, but there is public interest there in solar.
Yeah, and actually, there's a system installed in Alaska. I apologize if I forget the name of the community right now, but they are working to. They have a couple small hydro plants that are available, as well as they're looking to install wind and solar to supplement the traditional, more diesel generator type systems that they have running, because that area of Alaska, very high latitude, so they don't always get a lot of sun, and it is very cold. But it's also hard for them to get fuel transported. So there are some considerations for that. Typically, as the price of solar and storage comes down, it may be become more feasible to install enough solar that you'll be able to generate enough in those types of climates. But we're still looking into that.
Great, thank you. I had a question about thermal storage, which is an emerging topic, certainly at DOE. Have any of you investigated pairing thermal storage with the solar technologies discussed today?
This is Dave again. So we do have another team in our office that's the concentrating solar power team, and they are entirely focused on thermal storage and utilizing mirrors in terms of trough systems or power towers to run a more traditional type of power plant that's operated with steam. But in terms of other forms of thermal storage, there are discussions about different forms of using the building as thermal storage, or like heat pump hot water heaters as another form of energy storage. So you'll heat up that water during the part of the day when you have excess solar generation, so that you're not heating it as much at night when you're using it to run your washing machine or dishwashers and stuff like that.
Very good, thank you. Question from Ron, who asks, since energy transmission is regulated at the state level, as was mentioned, how do you see the future of microgrid implementation in the United States?
So there are some states that are more proactive than others in looking at resiliency and the ability to integrate renewables into microgrids. So a lot of the work that we're doing is definitely is focused on developing the technology, but we also want to make sure that we understand what those regulators, the types of information those regulators need, so that they can make the right decisions on policy changes for implementing microgrids. So I definitely think as there's more resiliency type events that occur throughout the country, more and more locations are going to be states, or even small localities are going to be looking into utilizing some of these microgrid technologies to make their communities more resilient.
Great, thank you. Question from Cleophas, who asked whether the microinverters available today can interpret and control data from solar, geothermal, and backup generators efficiently in a residential home.
So microinverters are, they operate just like the other types of solar inverters that are installed. They're just, they're much smaller and mounted directly to the panel, as opposed to an external unit which you run a number of a string of panels to. So those inverters are really just converting the power from the solar, and then there can be an external, another home energy management system controller that would then be looking at either your geothermal heat pump or any of the other controllable loads within your home. So the microinverter really wouldn't be the controller for that type of stuff, though.
Okay, thank you. Interesting question from Eliza for Andrew. Is there a way to use carbon to make solar panels? She is thinking about the carbon industry's potential loss of jobs, since there might be reduced extraction, but still existing extraction, but no burning to produce energy for power generation.
So using carbon directly for solar panels is not necessarily under heavy investigation, but you do see some groups investigating using carbon for electrodes within the panel. So it's part of the device stack that extracts the electricity from the panel itself. So there is some use there. Again, though, since there's such a low material requirement for these thin film technologies, the layers are so thin, it's unlikely that that's going to be a large enough market to substantially offset carbon utilization.
Very good. Thank you. I'm just looking through our questions queue. I will briefly note, since this was asked several times, we will be making a recording of today's presentation available. It will be sent via email to everyone here today and also posted on the Solar Decathlon Virtual Sessions website, along with all of the prior recordings. And you can also register for our lone remaining webinar on April 28th. And here, I think, is another good question from Robert. Regarding community microgrids, David, can you speak to the implications of integrating vehicle grid integration technologies as part of a microgrid configuration? Given the long duration parameters of EVs, such a resource could be part of a highly resilient microgrid system that can last indefinitely, assuming daily availability of renewable generation.
Yeah, no, that's a great question and a great path forward that we're also investigating with the Vehicle Technology Office. So Vehicle Technology Office here at DOE, they're more focused on developing the battery chemistry and the motor controllers that are used in those electric vehicles, and working with manufacturers to ensure, basically to allow those vehicle to grid operations. So right now, we view electric vehicles as a load because we need to charge them and make sure that during an event, if people need to evacuate, those electric vehicles are charged. But we're hoping that in the future, more electric vehicles will be available to use as an energy source, so that to supplement storage later in the day. Some of the concerns about that are that the battery chemistry that are used in those electric vehicles may not be conducive to running like high output for a long period of time, which is what would be needed in a community microgrid, but it's not necessarily how a vehicle is operated. And then there's another concern with the number of cycles, like charging and discharging of those batteries. If you're utilizing it for driving the vehicle and for running on the grid, you're utilizing that battery more often. That will definitely have effects on the lifetime of the battery, which the vehicle manufacturers are concerned about warranties with that. So we've definitely had conversations with the vehicles office on how can we better utilize and control those technologies as well.
Fantastic. Thank you very much. Thank you to all of our speakers and to our audience for your questions, and our speakers, of course, for their answers. We have about 1 minute left. I definitely want to get people out and about on time. So with that, I will turn it back over to Jonathan to lead us out.
Great. Thank you so much, Tyler. And thank you for all of the great questions from our audience. Really, really insightful questions. And thank you again very, very much to our fantastic speakers. Those are great presentations, extremely well organized, well structured, and just full of great information about all of the wonderful work coming out of our solar office. We really appreciate your time and your work. And with that, we're going to close this session in the Solar Decathlon series, and again invite you to join us next month for the last one. And with that, enjoy your day, and we look forward to being in touch on the next one. Take care.